Hello, and welcome back to Sensors and Sensor Systems. Today's mini lecture will focus on force-sensitive resistors and will provide an overview of the two major configurations of FSRs and the respective characteristics or performance metrics and applications for each. First, a little bit of background. The FSR has been around since 1977 and has evolved since then with advances in manufacturing processes to produce a wide range of FSRs made by different companies that are pretty inexpensive. Many FSRs are sold for less than $10 a piece in small quantities, which makes them accessible to a wide range of force sensing or pressure sensing applications. In general, the FSR is a sensor system. It consists of two major components: a pressure-sensitive polymer, which is responsible for providing us with a resistance that's a function of force, pressure, or stress, and also surrounding materials that make the pressure-sensitive polymer talk to us in the way that we can optimize their performance. So those layers may include metal electrodes that make contact to the pressure-sensitive polymer properly. They may include spacers that allow us to control when the sensor turns on in terms of the applied pressure or force, and other layers that basically govern how the pressure-sensitive polymer behavior is converted to a pressure-sensitive resistance. Most pressure-sensitive polymers operate by a process called quantum tunneling. And quantum tunneling basically allows us to have conducting particles within these polymers that don't actually touch each other, but when they get very close to each other, they nevertheless create a decrease in resistance the closer they are to one another. So when we use quantum tunneling as a governing mechanism for these polymers, what we see is an increase in conductance or a decrease in resistance with increasing pressure or force. In contrast, some pressure-sensitive polymers operate by a process called percolation, and those polymers traditionally have a much larger number of conducting particles contained within their otherwise insulating matrix, and because of this fundamental difference between the percolation-based polymers and the tunneling-based polymers, what we see is that conductance actually decreases and resistance increases with increasing pressure or force. Regardless of whether they're percolation or tunneling-based FSRs, these pressure-sensitive polymers can be configured within the FSR system in two major ways, either through what we call through-mode operation or shunt-mode operation. And in the next slides, we'll just go through each of those configurations briefly. In through-mode configuration, we have a very straightforward sandwich of materials. Typically, FSRs are made on flexible substrates so they can bend freely with applied forces and pressures and they don't break. That flexible substrate hosts a sandwich, and in the through mode, that means that we have two conductive layers, both of which are making contact respectively to a pressure-sensitive polymer. And typically in most FSRs, we already also have an adhesive or a spacing layer. And what that allows is to have infinite resistance at zero applied force or pressure. So that allows us to control the detection limit for the FSR and also to avoid interference effects from small forces or pressures that are not of interest to the application. Now, since through-mode configurations have two conductive layers, they end up being more expensive. And you may be wondering, well, a conductive layer, how expensive can that be? Well, the issue is that this conductive layer has to make good contact with the pressure-sensitive polymer, and that normally requires using silver or other non-trivial cost metal in order to make proper contact. So that's why when we use a through-mode configuration, generally they cost more because there's more metal involved in creating the structure for the FSR. Now, through mode FSRs, because of the nature that once they break through the adhesive or spacer layer, that the two pressure-sensitive polymers become in direct contact, they tend to have lower detection limits, higher sensitivity, higher accuracy, and smaller dynamic range than their companions in shunt mode configuration. Therefore, they're used in applications where it's necessary to detect smaller forces with greater accuracy. And one of the classic applications of this is the robotic fingertip. It's important that a robotic fingertip be able to hold on to an egg without crushing it, but also to be able to hold on to a bowling ball without dropping it. And that requires sensing the amount of force that we're applying to holding an object, which provides some means to make sure that we don't crush lighter objects and we can still hold on to heavier ones. Similar applications are musical instrument controllers, infusion pumps for IVs, augmented reality systems, force and accuracy detection, and a cell phone stylus, all of which don't require a lot of pressure to operate or force to operate, but require high accuracy and low detection limits to operate in a way that's useful to the application. If we want a higher dynamic range, we can use a shunt mode configuration. These FSRs based on shunt mode configuration tend to be less expensive than through mode, and that's because in the shunt mode application we only have one conductive electrode. And on top of that conductive electrode, we still have our spacer layer to make sure that we, at zero applied force or at small interfering forces, we don't see any response from the FSR. And we also have the pressure-sensitive polymer that is pressing up against now this single screen-printed interdigitated structure. And instead of creating direct contact across two pressure-sensitive polymers, what happens is the pressure-sensitive polymer ends up moving into the gaps between the interdigitated fingers and interfering with the existing resistance between those two sets of fingers. When it does that, we call it shunt mode because it's providing an alternative pathway for current to flow. So depending on the application, the interdigitated fingers that create this one electrode in the shunt mode configuration may have an insulator in between and have infinite resistance between the fingers. When the pressure-sensitive polymer intrudes, it shunts or creates a pathway for current to flow, thereby decreasing the resistance that's measured by the overall sensing system. This configuration, while it only requires one electrode, is also less sensitive than through mode because we're basically pushing material in between these interdigitated fingers rather than making direct contact in a direct resistance measurement. So in the end, these shunt mode FSRs are useful for applications where we need a wider dynamic range. For example, shoe insoles that are withstanding the entire weight of the human body. It's an application where you need a wide dynamic range capable of handling adult weight, but also where you don't need as high a resolution to understand the pressure and the forces that are being put on the foot as an individual walks or makes other motions. There are other applications in sports, monitoring both baseball and golf swing assists, again, a wide dynamic range, don't need a lot of accuracy, so a shunt mode resistor, shunt mode FSR, is far more attractive in that case than through mode. Typical transfer characteristics for a shunt mode FSR. What we see here is the point at which first there's some initial contact and communication or shunting between the interdigitated electrodes caused by the pressure-sensitive polymer, and then after that initial shock to the system, this is not an actually linear curve here because we have a logarithmic x-axis. So we see a sharp decrease for lower values of force, and at higher values of force we tend to see a shallower decrease in resistance. Nevertheless, a wide dynamic range is possible, and we can detect forces with limited accuracy across this entire dynamic range. So if we just look at a comparison of different FSRs, we see their accuracy is very all over the map, and the accuracy also depends on what type of pressure or force we're applying. The bottom line here is that what we see is that FSRs, while they're inexpensive and often very useful to a wide range of applications, they do require calibration in order to meet the needs of the application. So while the sensors themselves are inexpensive, the related development time as well as the signal processing required to maintain consistency in the FSR application can become quite burdensome. In summary, force-sensitive resistors rely on pressure-sensitive polymers, mostly dominated by quantum tunneling, but sometimes by percolation behavior, to operate and produce a resistance that changes in response to an applied force, pressure, or stress. FSRs can either operate in through mode, for detecting smaller forces with higher accuracy, or in shunt mode for detecting a broad range of forces at much lower accuracy. They generate a resistance that is the sum of the bulk resistance in the pressure-sensitive polymer and the contact resistances between polymer and contact electrodes. So that's just a brief overview of force-sensitive resistors. Thanks for joining us, and we hope we'll see you again soon.